Hi, I'm Yoav Columbus, and we'll talk about optimal collaterals in multi-enterprise investment networks. This is a joint work with Moshe Babayov and Eyal Winter. So we'll talk about settings where there are firms that raise capital from investors. And these investors, they are facing strategic risk in the sense that their gains or losses may depend on the actions of other investors. And we'll talk about collateral contracts as a mechanism design tool in these investment games, and about investment networks, which I'll present. So let's start from an example. Let's say that there is a firm that raises capital for some enterprise. And this firm needs to raise at least $4 million to cover the costs of this enterprise. And the total returns for investors are going to be the total investment amount minus the cost, and this is going to be multiplied by 2, which is some interest, 2 in our example, and that is if the cost is covered. If the cost here is not covered, then there are going to be 0 returns to investors. And the total return is going to be divided between the investors proportionally to their investment amounts. Well, let's say that Alice, Bob, and Carol represent firms that consider investment opportunities of $3 million each in that enterprise. So in the drawing here, the arrows point in the direction towards the investors, so it's in the direction of the returns. And this is going to be a one-shot game in which every player needs to decide whether to invest, which we call cooperate, and then he will get whatever he gets from the returns, or not to invest, which we call defect, and then he can keep the investment amount. So let's look at some investment scenarios. First, if Alice invests alone, then the total investment is $3 million, and this doesn't cover the cost of the enterprise. And so there are going to be 0 return for Alice, and Alice would prefer to defect and keep the $3 million. The second scenario, Alice and Bob invest, but Carol defects. And here the total investment is $6 million, which does cover the cost. So the total return is $4 million, and the return for Alice is going to be $2 million, and so Alice still prefers to defect. In the third scenario, everyone invests, and here the total investment is $9 million, and I'm going to claim that this is an efficient, going to be an efficient outcome. The total return is $9 million minus the cost times 2, which gives $10 million. And here Alice has profits, so she prefers to cooperate. So some basic observations from this example are first, that indeed there is a game between these investors, and all cooperate, the profile where everyone decides to invest, is a Nash equilibrium of the game. But all defect is also a Nash equilibrium, and this is not an efficient equilibrium. So we're going to ask how to induce a unique equilibrium of full investment. And we're going to use collateral contracts and study how they can do that. And a collateral contract is a financial instrument that aims to give security for investors. Of course, securing collaterals has some cost, like buying insurance, and a firm would prefer to give less collateral if it can. So, the types of collaterals, collateral contracts, we consider they provide limited insurance for an investor for the invested amount. If there are going to be profits, the return is more than the investment, then the collateral is not realized, and the payoff of the investor is just the return from the investment. But if there are losses, then the payoff for an investor that has collateral of amount C is going to be the return, whatever he got from the investment, plus the amount of the collateral. But this is going to be kept at the investment amount, because this is only insurance against losses. So let's look at some investment scenarios now with collaterals. So first, let's say that Alice has a collateral of $500,000. In our first scenario where she invests alone, still the investment doesn't cover the cost. So she has 0 returns from the enterprise. But her situation is a little bit better because she has a utility of $500,000 because she has this collateral. The second scenario, Alice and Bob invest. total investment as before is 6 million. Alice is going to get $2 million from the return, and she has also $500,000, additional $500,000 from the collateral. So she has 2.5. And in the third scenario, everyone invests. As before, Alice has profits, and so the collateral is not realized. Now let's look at a different scenario where only Alice and Bob invest, but now Alice has a larger collateral of $2 million. So what should Alice do? Alice here has a utility of at least $3 million anyway, because she's going to get $2 million from the enterprise, plus $1 million from the collateral, so exactly $3 million in this scenario. So here she prefers to cooperate. We assume a tie breaking in favor of investing. You can think about it as some additional epsilon utility for investing. So how to induce a unique equilibrium of full investment? Let's look at the following collaterals in our example. Let's say that Alice has a collateral of $3 million, and we call this a full collateral because it covers the full amount of her investment. And Bob is going to have a collateral of $1 million, which we call a partial collateral, because it covers only part of the investment amount. And Carol is not going to have any collateral at all, so zero collateral. So what is going to happen here? Now, Alice has a dominant strategy to cooperate because she gets at least $3 million because she has a full collateral. Now, Bob knows that Alice is going to cooperate, and he knows that in this situation where they both cooperate, his return is going to be at least $2 million. But he also has this $1 million collateral. So the utility for Bob is going to be from cooperating at least $3 million, and he also prefers to cooperate. Now, Carol knows all this. She knows that Alice and Bob are going to cooperate, and so she prefers to cooperate as well, reaching to the all cooperate strategy profile. So we get that all cooperate is a unique mesh equilibrium with these collaterals. It's easy to see that it's unique because what we just did is iterated elimination of strictly dominated strategies. So it must lead to a unique equilibrium. And the total collateral here in this example is 4 million. And in fact, this is optimal for this example. You can't give any less collateral and secure a unique equilibrium. And so the problem that we define and analyze is the collateral minimization problem that asks to find the minimum sum collaterals to induce a unique equilibrium of full investment. And this is going to be challenging for various reasons. First, there may be many investors, heterogeneous investments, and so this may become combinatorially complex. You need to figure out how to define and solve an optimization problem. And second, we're going to look at investment networks. And some of the investors may actually be capital raising firms themselves. They may have their own enterprises. So the situation may look more like this. And in this case, investors can reach a state of default if they don't manage to, if they are capital raising firms and they don't manage to raise sufficient capital to cover the costs of their enterprises. So they may reach default and be unable to invest. So players need to think not only about whether their co-investors are willing to invest, but also if they would be able to invest. And this adds strategic risk that may propagate in the network due to the risk of default cascades. And I'll demonstrate default cascades just now. So let's look at this toy example, this network, where the nodes that are marked with numbers are firms that have their own enterprises and they are raising capital. Let's say in this example that every firm, every capital raising firm needs all its 3 investors to cover the costs of its enterprise. And let's assume that one of the players here on the top left decides for some reason not to invest. So what's going to happen is that firm number 6 is going to reach a state of default because the cost is not covered. then firm number 6 will not be able to invest in the enterprise of firm number 5, which is going to be in default as well. And this propagates to all the enterprises in the network in this example. And so notice that these players here on at the bottom, when they make their decision, they need to consider not only the decisions of their co-investors in the same enterprise, but also the decisions of, in fact, all the other players in this network. So this is a network effect and things become more complex. And we're going to ask what are the effects of network structure on the optimal collateral scheme. So overview of our main results. First, we have results that are general to any network, general characterizations. And then we make a distinction between cyclic and acyclic investment networks. We show that the situation is quite different in these two settings. So for the general characterizations, first, we show that a unique equilibrium implies dominant solvability. Whenever you can induce a unique equilibrium using collateral contracts, then this unique equilibrium must be reached, or it must be reached by iterated elimination of strictly dominated strategies. The game is dominant solvable. And then we talk about existence of solutions by collateral contracts. We show that there are networks where a solution does not exist. And we show that solvability can be determined in polynomial time. And in fact, we show exactly how you can identify problematic structures in the network. You can read more details in the paper. And we also talk about computational complexity, and we show that in its general form, the collateral minimization problem is NP-hard. And the intuition is that if you have many investors in the same enterprise, then you're facing a kind of a knapsack-like problem where you need to decide which investor is going to get the larger collaterals. So this is basic intuition. And when we look at the acyclic networks, we have these results that say that in any acyclic investment networks, first, a unique equilibrium can always be induced by collateral contracts. And second, if the degree in the network is bounded, if the number of investors per enterprise is bounded, then there exists a polynomial time procedure that we show exactly to calculate the optimal scheme of collateral contracts. And third, we show that the network structure does not necessitate, in fact, any excess collaterals. So this additional strategic risk from the network does not require additional collateral. In fact, the collateral contracts that are optimized for each enterprise independently, ignoring the rest of the network, form together an optimal scheme for the entire network. Now, when we look at the networks with cycles, things are different. First, there exist networks, investment networks, where a unique equilibrium cannot be induced by collateral contracts, even if you give full collaterals to all investors. And we show, as I said, exactly how to find these cases and characterize them. Second, when you have cycles in the network, the collateral minimization problem becomes NP-hard even for bounded degree networks. And finally, even in cyclic networks, even if you have a solution and you can find it, we show that the total collateral in an optimal collateral scheme may be arbitrarily higher than the corresponding non-network environment, where the sets of investors and capital raisers are disjoint sets. So in conclusion, we study investments in networks, and we study the role of collateral contracts to affect these investment games. And we define the collateral minimization problem that asks to find the minimum collaterals to induce full investment as a unique Nash equilibrium. And we show that in acyclic investment networks, a solution first always exists. And then collaterals can be optimized for each firm independently, ignoring the rest of the network. And there are no added collaterals due to the structure of the network. So the same collaterals would be given also in a non-network environment. And in cyclic networks, we show that the solution does not always exist, and cycles can increase the minimum total collateral that is required. And finally, in cyclic networks, cycles imply further computational hurdles. Thank you.